We are here to start with the new topic of springs. Springs is basically that we install in every mechanical equipment. Here the purpose is to explain you the types of spring, what is their function, how we design a spring, and how we practically install that spring in the particular application. So springs is basically for the 5 application. Let us discuss that one by one. First of all is to the shock absorbing. So the shock absorbing, and second is as it does in the carrier spring. Next is to store the energy, for the example in the clock springs. Third one is that to apply the forces to control the motion as we do in the brakes and clutches. Next is to measure the forces as we do in the spring balances. Next is to change the variation characteristics as we do in the flexible motors. So the material for the springs is medium carbon steel, that is carbon up to 0.28 to 0.58% carbon, and in the high carbon steel that is up to 0.7 to 1% of carbon. These are the springs where we use where normally the springs is required, but where we are having the problem of corrosion, we are dealing with the springs of phosphorus, bronze, high speed steel, stainless steel. So this type of steels we use for the corrosion resistance problem, where we require corrosion resistance. So we basically divide the springs in 6 different categories. First is your helical spring, leaf spring, circular spring, torsional spring, belly spring, and flat springs. So in today's class we will be just covering the closed spring. In the helical spring we are having 4 categories: closed spring, open spring, tension helical spring, compression helical spring. So in the leaf spring we are further having 3 categories: elliptical springs, semi-elliptical springs, and cantilever springs. Today we will be just covering the closed spring. Let us assume it is a spring. Now we will be dealing up with it. In today's class we will be dealing up with the open helical spring. We know that it can show some deflection if we apply a load. We are having few constants which are involved in the open helical spring. First of all, it is the diameter of the spring, capital D. Okay, if we divide it by 2, we get radius, that is capital R. We applied the load W onto the spring, which is capital W. D is the diameter of the coil, that is diameter of the spring. This is the diameter of the spring, capital D. This is the diameter of the coil, small d. Now, when load is applied onto this spring, we get a deflection, that is delta. When we apply a load, there is always there will be a twist, which is called as theta. Due to this deflection, due to this twist, there must be a stiffness in the spring, that is K, the small k. L is the length of the spring, 2 pi r n, and shear stress is, you know that you have already done in the torsional equation. So G is the modulus of rigidity and W is the load applied. So let us see its derivation of the open coiled helical spring. In the open coiled helical spring, we are having the torsional equation T over J is tau by R equal to G theta by L. We will use T over J Fs by R as first relationship to calculate your shear stress. Second relationship, T over J is G theta by L to calculate the twist. Okay, so T over J is G theta by L, Fs by R. We know the value of polar moment of inertia J is pi by 32 d4, and R is your d by 2. So we get a relationship as we do in the torsion of shafts. We have done this relationship earlier. I will not go in detail for this. So we take the value of tau over 16T by pi d cube. We know that torque is always equal to the force into distance. Here force applied downward direction is W, up to the distance of force is applied up to the distance of R. That means W into R will be the value of torque. So we put this relationship and get the relation for the shear stress. Similarly, we get a relationship for the twist, that is theta. T over J is G theta by L. Now T is W by R, J is pi by 32 D4, G is your constant, that is the modulus of rigidity, which will be given to you. Its value for the stainless steel is nearly about 80 to 90 gigapascal. Theta you have to calculate, L is 2 pi Rn. So we get the relationship for the theta, this one. We know that to calculate deflection, which is equal to, deflection will be equal to R into theta. R is the radius of the spring. And you have calculated theta, so deflection can also be calculated in this relationship. So now, further we come to the relationship. Now we have calculated the shear stress, deflection and twist. Now we come to the fourth term, that is stiffness. Stiffness is basically W by delta. W you have already know that it is the load, and delta you have already calculated, so you just put the values. You get the stiffness. Strain energy stored, you have also covered this topic earlier. So we use this relationship, that is 1 by 2 into T into theta. T is W into R, theta you have calculated over here. So you get the relationship 1 by 2 W into deflection. So in this relationship, from this derivation, we have come out with 5 outputs. First is shear stress. Second is your deflection, third is twist, fourth is stiffness, and fifth one is the strain energy or the energy stored. So these 5 values you have to calculate in either form. Something will be given, something will be missing. You have to find out these 5 values always. Sometimes diameter will be missing. So in that case, a relationship between small and the larger dia must be given. So you can calculate that. Let us see one numerical. If load is given to you, diameter of the spring is 10 times the diameter of the coil. For this case only, it is not generalized, it is a numerical. Shear stress is 80 megapascal. So you have to calculate small d and capital D. So you can simply put your shear stress is given to you, put the value over here. Your W is given to you, you can simply calculate the relation between capital R and small d, because capital D is 10 times of the small d. So this numerical can be sorted out. Second numerical. These are all of the open coiled helical spring, very easy numerical. On these 5 relationships, you will be solving up the numerical. If you know the 5 relationships, you can easily do any calculation for open coiled helical spring. So now, small diameter is given, larger is given. Earlier it was missing. Number of turns is given for the spring. Your G value is given to you. Modulus of rigidity, deflection is given to you. You have to calculate K and W. For K, you are having one relationship. For the W, you are also having one relationship. This one, because deflection is given. So you use these 2 relationships to calculate. We have done the calculation of this in class, which is coming out to be stiffness. Stiffness value will always be in Newton by mm, Newton by meter. You just see over how the answer is coming out to be. And your load will be equal, it will be in newtons. Your diameter will be in mm. When you solve the question, just keep these things in your mind. Similarly, the third question. In this question, you have to calculate all the 5 relationships. That is your deflection, your twist, your stiffness, your strain energy, and your shear stress. Diameter is given, N is given, diameter of the spring is given, and separately for the coil is also given. G value is given. So you can use all the 4 or 5 relations which we have used for the derivation to calculate these values. So basically, out of these 5 relationships, you can easily calculate any numerical related to open coil helical spring. So in this case, we are finished with open coil helical spring. In next class, we will be doing up with the closed coil helical spring and your elliptical spring. Any doubts? Thank you. Discuss the topic of your
coil helical spring.
Which one? We are going to cover the case where the helix angle is involved. Now we are taking a case where this is a spring, one of the coil of the spring, diameter D, load W has been applied towards the downward direction. Helix angle alpha is the angle which is made up with the horizontal. So now what we have done, we have taken this length, calculated this length from the Pythagoras theorem, coming out to be 2 pi r secant alpha. So now you know that when load is applied onto a spring, what happens at that time? Two types of strain energies are involved. First of all, the work done has to be equated to the strain energy by movement and strain energy by the torsion. So let us take strain energy due to the bending, that is m square L by EL. So similarly, strain energy for the twisting will be T square L by 2 GJ. You know that m is the movement, L is the length, your E is the Young's modulus, and your I is the moment of inertia. Similarly, strain energy for the twisting will be T square L over 2 GJ, where T is the torsional force, L is the length of the coil, which will be taking as 2 pi r secant alpha, 2 pi r secant alpha. If it will be having number of terms, we will multiply with n. So next thing is that length, you know, 2g is that is J, polar moment of inertia. G is the modulus of rigidity. So now you know that work done will be equated to the strain energies, because what is the work done has to be stored inside the spring. So W into delta is equal to the work done by the movement and the torsion. So we equate the work done with this movement and torsion. We calculate the value of the deflection, that is the downward movement caused by the helical spring. So now I equated these two equations, put the value of M as W into R sin alpha and T as W into R cos alpha. Why? Because the movement has to be applied upon the vertical axis, because movement is applied upon the perpendicular axis. Torsional effect is acting upon the horizontal axis. So we applied these two values, WR sin alpha, WR cos alpha, in the respective of your movement and torsion. So we get the values of the deflection, which is coming out to be 2 pi r NW secant alpha bracket sin square by E by plus your cos square by 2 GJ. So finally we have calculated the deflection. Similarly, you can calculate the angular rotation also by this relationship. I have directly put the value for the angular rotation, that how much is the spring has been rotated during the applied of the load, which is due to the movement and the torsional force. So this is the value of your axial rotation. So now we have covered the cases of open helical spring, closed helical spring. In the closed helical spring, we have involved with the new term, that is your alpha, and that alpha is called as the helix angle. There may be the different cases. This is the case one in which you are calculating the deflection and angular rotation. There may be the cases you can have to calculate your alpha, that is the helix angle. There may be the more different number of cases in which you may be finding the radius of the spring. You may be calculating the diameter of the wire or the coil of the spring. So this was all about the closed spring, the case of the your helical, that is the helical angle is involved. So any doubt in this? Okay, thank you.